Okay, so today we're going to talk about some concepts around continuity and one-sided limits. Um, First thing, if we look at a graph, okay, and I'm just going to make one up. Okay, this graph here, obviously we can look and see that everything's connected and everything's nice and smooth. Um, that's normally a good sign that it's continuous, but basically everything is connected. Keep that as in mind. That's really what continuity is all about. Um, Now, the official definition, if we look at every point on the graph, so at every point, but more specifically, if we were thinking about continuity at a point, are we continuous at this particular little red dot here? It depends on three factors. Our first factor is going to be um, is is the point defined? Okay, so basically, is it even there? Now, obviously, we've got this whole, or it's filled in, so we're good. It is there. Two, um, we're bringing in this idea of one-sided limits. Okay, so um, basically, or excuse me, does the limit exist? Does it exist? Well, in order for a limit to exist, and we're going to get to this in just a minute, um, you have to approach the same number from left and right. Okay, so it doesn't have to necessarily be there, right? These two things are not inclusive to each other. Like they don't have to both happen. This point could be up here, but the limit would still be at the red dot so long as they're agreeing that that's where they're going. They're going at least where the red dot is or where that area is supposed to be. Um, so this is good as well. The limit does exist at this point. Now, the third thing basically says that the limit and the defined point must match. Oops. So in other words, the limit, so where the function looks like it's going and what the function is both have to agree. So now, most functions that are like that. But let's say, for example, we had, instead of this function here, let's say I did this. Okay? Well, this function, okay, if we're looking at this point up here, all right, and we go down our list, is the point that we're looking at defined? Well, based on our function here, we don't see this dot appear anywhere, right? There's nothing here. So no, we wouldn't be defined in this case, or we wouldn't be continuous because that point doesn't exist anywhere to start off with, so it can't be continuous. Now, if I put this dot anywhere else, so let's say I put it right here. So first off, is the point defined? Well, yeah, it's defined, right? That's good. It's right up here, and then we go, does the limit exist? Well, from left and right, we're going towards that empty hole, right? We're going there, so the limit does exist. Oops. So yeah, we're good there as well. But the limit and the defined point must match. So in one case, we have our limits have to agree. Now, in this case, we've got both of the limit is right here, right? It's all pointing to that spot. But our defined point is up here. So we fail at this. This is where we fail to be continuous. So all three of these things must exist in order for us to be continuous. So we've got to have a point defined, we have to have a limit that exists, and the limit and the point have to match. For one-sided limits, so we were kind of getting at that the last time. So one-sided limits look like this. Let's say, let me draw another graph. Okay, very similar to what I did last time. And I'm going to make my little red dot. Okay, so one-sided limits are like this. If I'm coming from the left side, okay, we call this the limit as x approaches, and we'll call this point C. And I'll do that in red just to, as it approaches C of, and we'll call this f of x, that we need to know if this exists. Okay, now if we're looking at a particular side of that, so just this side, not both like we have here, this refers to a two-sided limit. A one-sided limit would just be looking from one side. What does it look like we're going to from the left side? We denote that left side by doing a little minus sign. That basically means values that are under C. They are before C, so they're smaller value than C. So this equals some number, right? And so we're going to call this L, right? So it roughly equals L. Well, we can also denote from the other side as well. So we go x approaches C, but this time we're going to come from the right side. So we denote that with a positive number. So numbers that are basically larger than C, or slightly larger. And that, in this case, right, it's agreeing that equals L. Well, if these two things work, right, if these two things are true, okay, then the limit as x approaches C of f of x. Okay, sorry about that. So the limit as x approaches C, so the whole thing, not the one-sided limits like up here, but overall the overall limit. So from both sides. Um, if these two things are true, if the left and the right both point to some number L, right? Their limit is L, then our overall limit is going to be L as well. Okay, and so as I was saying, if these two agree, then this has to be true. Which, conversely, if this is true, then this has to be true as well. So it's a pretty powerful statement, when you have this kind of biconditional statement where if this is true, then that is true, but also it works in reverse. The last thing we're going to talk about is the intermediate value theorem. This is sort of an obvious thing that you would think about, but it's pretty powerful, and it helps us do a lot with algebra and many other things. So if I had a graph, again, like this, I'm just making this graph, that's me. What it says is that if I have a continuous function, so, if continuous, so that's why this continuity business is very important, because if we know something is continuous, we can say several things about a graph. Where if it's not continuous, we can't necessarily say that. So if continuity exists, right, for f of x, what we can say is the following thing. And this could just be on any interval that it exists, but we won't get into that much detail right now. That if we pick 2 points, so I'm going to pick, I'll pick this point here, and I'll pick this point here. What it says is that there has to exist a point in between these two that has a y value that is in between the y values of these two. So think about this. So we kind of break off our little grid here. basically what it says is that I've got, if I take these 2 points, then there must be a point that is in this box that the function has. It has to be there. It's pretty simple, right? There must be a point in this box somewhere. Now, obviously, you can see there's a ton. It's really useful. It's very, very useful most times when we're trying to find zeros, right? In this function here, we've got, this point, is positive. This point here is negative. Well, what lies in between these two? 0, right? 0 lies in the middle. So I know that between these 2 points, because if my function is continuous, I know that in between these 2 points that I have a 0, which I do, in fact. So this has been used to prove several things throughout time, but it's a good concept to know that if a function is continuous, it has to go through every value between any two. It has to go through every single one at some point in time. So if it goes from negative to positive, we know that it has to cross 0. It's something that we use a lot in calculus, especially when we get into derivative work. But it's a very important theorem to know.